So you would like to put yourself at mute. And I request that you ask the questions while I'm teaching. Don't hold the questions till the end, because if you keep the questions in the chat box, what exactly happens that I may never take it because I don't see the chat box. Earlier, I used to regularly see the chat box, uh, but now I don't get time, and I get really, go to the next things. When this class ends, then I have to move to the new things. So I request you to please ask the questions while uh, I'm teaching. Just unmute yourself and go ahead. Absolutely no problem. And in case sometimes students have questions regarding some other technique, so then you can email me. So still there are many questions which are pending because that require another lecture series. Uh, I mean, probably those questions are related to uh, X-ray diffraction or something. And I will be selectively, I have some advanced things to teach in transmission electron microscopy. So that I will be teaching to select users, some really advanced people, stuff which will go into the quantum mechanics. And so that will be optional. Probably I will offer that when this module, basic module teaches. So this is basically elementary level, whatever I'm teaching. Uh, AFM was also elementary level, and AFM is also entry level course, and TM was entry level course. So advanced level, if somebody is interested, so that will be the second module. And same thing for Raman. It is going to be a very basic course because I have to finish with the exams of the students. And if I take them to more, deeper, so then it's going to be problem for them. So that's why I have decided. So, uh, Shabdiji, if you find this talk a bit too trivial, so please excuse me, because my students from NCL, they are from chemistry background, and those are my first, I'm serving them, that they are my first responsibilities. And yeah.
Don't worry, Professor. We will learn the basics as well. Go ahead. It's a good to learn. Thank you.
Yeah. So, sorry, there is some crashed actually. My presentation crashed. Hold on. So today I will be teaching some very basic modes of atomic force microscopy: contact mode, tapping mode, and non-contact mode. These are the three most popular modes. In fact, out of these three, contact mode and tapping modes are highly used. And let me move to the next slide. This content of this slide has been already discussed, the history of AFM, but this is the recap of the history, how things develop. But I always love to connect with what is, what was the contribution of our great scientists. So 1981, as you remember, that Beening and Rohrer invented first scanning probe microscope. Uh, basically that was scanning tunneling microscope, and but we call it as a scanning probe microscope because probe can be anything. You will see in the next slide. Uh, so in after 5 years, as you know the history from the earlier class, that Bini collaborated with Kuwait and Gerber and then invented another version, atomic force microscope. first it was contact mode, and a year later, non-contact scanning mode was introduced. Another year later, finer computer control was introduced, because ultimately you need to control it to the feedback loop. Still, the deflection of cantilever was being monitored by, I would say, that STM tip. Okay, I'll show you how it was being done. So basically, the main problem is that how do you know the position of the cantilever? Because cantilever is checking the force. Basically, it is sensing the force, whether it is attractive or repulsive. So then came the fabrication of AFM cantilevers. So 1991, the silicon industry started fabricating the tips, basically whether it is the doped silicon or silicon nitride tips. Uh, Last time we learned that silicon nitride uh, tips are more favored for contact mode, and silicon doped silicon probes are favored for tapping mode for different reasons. We can discuss it again. So 1993, another better version, intermittent contact or tapping mode. Tapping mode is a priority term, so intermittent contact is much more popular term. So here, some of the, so I'll be following intermittently Eaton and West book, 2010, published by Oxford University Press. That is the main book, and I'll be taking from different vendors' sites. Whenever I get time, I try to, as Siddharam Sabadi's mentioned, that his company. So I would love, many times I do this justice, I think, to check the vendors' website and see what they are offering. Sometimes they have very good application notes. In fact, I have learned a lot about AFM from various vendors, Bruker, NTMDT, and JPK, and all kinds of companies. So there is rich information. So that's why it is very important to invite the vendors and give them platform and let them speak. This is the integral part of learning. Please believe me, it's not just, if I just teach, it is, my teaching is incomplete unless vendors come with the product and tell us what are they selling actually. So please believe me, because they complete this any the sophisticated course like atomic force microscope. And next thing comes data analysis, and through some softwares that is already being planned. Some of my students have volunteered. I thought that they will also. Last year I taught myself, but I'll be watching, and probably they will be also happy to teach you, some of the senior students. So let us look at the, by the time you might have looked at this slide while I was talking on different issues. So first comes the AFM. You can see the richness of this technique. I mean, it is mind boggling. And this list has grown up in last 10 years. Probably this list was prepared sometime in 2009 by Professor Eaton and Professor West. And then this book got published in 2010. But 10 years down the line, this field has grown, as Shabadiji will probably showcase his product. So contact mode, non-contact mode will be covering today, intermittent contact mode. And chemical force microscopy, I'll be teaching in the next lecture. It is quite complicated mode, because you have to do it in a environmental control chamber, because chemical force are very subtle in nature, piconewtons, and you need to really take care of the capillary forces. Otherwise, you can't measure the chemical forces. Lateral forces will be covering today, whether it is LFM or frictional force microscopy. And these, in this bracket, different types of names like intermediate contact or amplitude mode or tapping mode. Different names are there basically by different companies. They are all given there. Reactive force, I'll be teaching to select few. There is one dedicated. Believe me, there is no shortcut for the learning. So I'll be teaching in the advanced module, and magnetic force microscopy, electric force microscopy. Force spectroscopy, it's highly important. I will see whether I'll teach, because it requires at least 2 lectures, 3 hours actually it requires. All these modes require at least 1.5 hours. Camel probe requires again 1.5 hour. Scanning thermal microscopy, I don't teach because I have no experience. And I mean, I would say that I've never used it. Nano oxidation lithography, that was one of the first thing I used 20 years back. Dip pen lithography, these are all small things, and that you will understand while you these things proceed, probably in the next lecture. Snow, I'll be teaching in a dedicated lecture, whether it is evanescent field and so on. And because that connects to a little bit to the Raman also, because integration of optical tech, near field optics actually, there are far field optics and near field optics, and this area is gaining a lot more popularity. So if Siddharam Savadiji has got a dedicated person for this kind of a thing, I know some of the companies are very strong here in this area. So I would love to give them a platform to teach, because this is very important for chemistry students also. Finally, STM, I generally teach to hardcore physics students, so that will be reserved for advanced modules. So I'll not be teaching in the for NCL class. So let us come back to the basics. Basics are very simple, that you have a silicon or silicon nitride cantilever, and which has got a sharp probe at the end. It can be conical, it can be pyramidal, it can be cylindrical, it can be a spherical also, it can be a sphere also. It can be without tip also. The cantilever doesn't need to have this tip. And it can be a nano wire, it can be carbon nanotube. So people are coming, it can be a diamond tip also, it can be coated with the gold or some other conducting material. So people come out with their own imaginations actually. There's no rigidity that it should be in a particular way. That gives it, it can be a thermal, there can be a temperature sensor here. Please believe me, here you can put a temperature sensor. So when you move this over the surface, you are essentially measuring the temperature profile the way you measure the body temperature by the this IR during this COVID period. So same way, you can just imagine that instead of this basically the gun which is being projected over your forehead, it is being projected at the sample, and this can be done in near field. I mean, there are various ways to do this thing, and the challenge is basically to increase the lateral resolution. That is the challenge. Whether it is a scanning thermal microscopy, it can be a capacitance measurement. So basically, you would like to measure the capacitance between the tip and the sample. Another thing that you can
can I just add one small point, Pankaj?
Yes, please.
Basically, you can, I mean, depending on what application you would like to do, instead of a tip, you can also attach a protein using some kind of a linker, and then study either protein-protein interaction or protein-DNA interaction. You are trying to say that it can be even tipless, it can be many other varieties of applications. I just wanted to mention that you can even attach the live to study the live cell studies using some kind of a protein, using a binder and things like that. I mean, applications are simply unlimited. Thank you.
Thank you, sir. Thank you very much. So we'll move forward. As Sri Shabadiji mentioned, that you can functionalize this, and you can chemically functionalize it and look at, for example, COVID problem. So COVID has got this spike protein at the surface, and then it has got a special affinity to certain proteins in the epithelial cell, lung cells, or pancreatic cells. So, I mean, this type of experiments can be easily done in the laboratory conditions. So, complementary proteins can, ligand and receptors can be coated on different parts, different surfaces, and then basically you can see their affinity, whether spike protein is, what is the reason that spike protein is so selective to certain surfaces. So this is interesting problem for atomic force microscopy for coronavirus. It doesn't need to be. I mean, you can take synthetic viruses which are harmless. So there is no RNA inside. There is no genetic information. It's just a shell, and what matters is basically just the spike protein. Inside there is no genetic material. So those kind of things are very interesting for like model studies. Why this basically coronavirus is so lethal because of the spike protein. All of you are aware of that. Obviously, the RNA material, RNA replication is a secondary thing, but the primary thing is basically its affinity to the body's different cells. So it just get hooked to so well that that's what we say in the layman term, that it is so it's so infectious. Infectious means its entry to the mammalian cells is so easy because of the spike protein. Anyway, so this kind of experiments can be, that's what Mr. Shabadi was mentioning, that this kind of experiments can be planned as per the needs actually. So this is another application. So what we do currently, most of the companies, they shine a laser and then this laser bump off the apex of this cantilever. So this is quite, as I told you, that I can teach for 1 hour about just this aspect, that laser, where the laser should hit, and if the laser hits here and there, so what will be the consequences. It's a very serious thing. Let's not dive deeper in this class. Uh, so if you further zoom, then we see immediately that this is the tip model and this is the surface model. So so when both the tip and surfaces, they are at a certain distance, so collection of atoms from the AFM tip and collection of atoms from the surface of the samples, they interact with each other through variety of forces, which we have already discussed in 3 separate lectures. I hope you remember that. So now the question arises that what is the reason that AFM can give you uh, basically sub angstrom resolution images, because the tip looks so blunt usually. So tip has got this asperities, basically sharp asperities. So one of those asperities and atom, few atoms, they interact more strongly than the other areas. Essentially you end up interacting less number of atoms to the surface from the tip. So that gives you a better resolution than what is expected. And the problem is here that if these asperities are so fragile in nature that you may you may end up modifying those surface asperities when you scan the tip over the surface. So tip doesn't remain the same. So that is the effort that, suppose you are doing a very serious experiment, molecular resolution. So you have to be very careful that you don't end up modifying the tip radius itself. Otherwise, it will be quite problematic for the calculation. So earliest deflection sensitivity was done by another STM. So you can see that this is the, I think somebody asked me earlier. So this was one of the original design, that you have this gold foil cantilever, and probably you can have this diamond tip attached to that. And then you have, how do you measure the deflection of this gold foil cantilever? Simple, because it's conducting, so you can put another gold STM tip, and that is ultra sensitive. So you have basically, you're measuring the tunneling current. So when this cantilever moves up and down, when it moves up, so this tunneling current will increase sharply, exponentially, and when this cantilever moves downwards, so this current will exponentially decrease. So based on this interaction, one can essentially measure the surface topography, because the forces are going to be different when the tip scans over this rough surface. So this was one of the earlier design. So, but people have moved. People try to experiment in various ways. So you can see that This was the earliest design in Dienig's paper in 1986, PRL, when the AFM was invented. And next year, Martin et al., in 1987, they used optical fiber. Finally, in the same year and 2 years later, this laser, use of focus laser became popular. And along with this photodiode, quad photodiode, this is there are two photodiodes, but essentially we take four photodiode assembly of that. And one can also use capacitance measurement because that becomes highly sensitive. You know that capacitance is highly sensitive to the interlayer, cathode, inter electrode distance, and that's a smart way of doing the distance measurement, capacitance measurement. I hope you're aware of that. So capacitance undergo tremendous change. Another way is basically you can do piezo resistance measurement. So there are various ways of measuring the cantilever deflection. So this laser is not the only way. That's what I wanted to tell you. So suppose you have to design AFM in your own backyard. So you can experiment with various things actually, as simple as that. So this is quite user friendly setup. So many times students end up designing AFM in their backyard, and that is simple. So many of the kits are available on Amazon, and the open source softwares are there. So it's not a rocket science to design your own AFM actually. If you are really motivated, you can do that easily. So this is a generic scheme that you have either sample movement or cantilever movement, either way, but you have to have some kind of feedback system. So that tells you, it's like a balloon ride over the city of Pune or Mumbai, that you have a hilly area and you would like to maintain certain distance as a safety measure. That, for example, somebody tells you that you have to fly around 50 meter above Pune surface. So when you encounter a hill, then you have to move the uh, balloon by. So there is this mechanism is called PID. P stands for proportional control, I for integral, and D for differential. So this is the way all the even temperature, all the furnaces, everywhere wherever you want finer control, that is done. So in my PhD, we used to make PID circuit. We used to make even softwares to control ourselves. Now you have this PID controller available, but that used to be a very fun electronics for us to make our own controller and write program and all kinds of things. So this has been introduced already, the scanner part. So I'll move on, and tips and cantilever. All these things have been discussed earlier. Controller has been discussed in the last lecture, and so I'll move on. Actually, I think parts are already discussed. So we'll go to the basics now. So what are the differences in STM and AFM, their functioning, and that has to be understood very well. The physical picture is as follows: that STM, essentially you are doing the current measurement. So these are the tip states, dense tip state somewhere, here you have, and it depends upon what kind of tip you are using, whether it is S wave or D wave, last atom, whether you are taking, so that will be discussed there, what kind of density states you have. And then you have the surface and there is particular distance. So here it is, you can see that it is easier to make a feedback loop for STM because it follows certain exponential relation. So the moment this distance is decreased, so basically current always increases when the distance decreases. So that is easier to calibrate actually. But if you look at this bottom schematic, you realize that in the force spectroscopy, in fact, we just take Lennard-Jones potential or combination of repulsive and attractive force. You can see even that part is quite complicated. Forget about integrating other forces, like you might have strong capillary forces, electromagnetic forces, combination of different forces, a khichdi, then this curve become quite complicated. Even to understand this curve is so, because you can see that somewhere here you have a bond formation where you have equilibrium. When you have a bond formation, that means forces are at equilibrium, force is zero. That's why you have a stable bond formation. So then if you go closer to, if you reduce the distance, you enter basically repulsive force because of Pauli exclusion principle. So the force becomes repulsive in nature. So contact mode basically works in this region. So probably in contact mode, it is easier to uh, you know make some feedback loop, because unless if you're in this region, so you know that if you take this region linear, and I will tell you in the force spectroscopy how this region in what circumstances this force distance curve, this area can be linear and this can be non-linear. Sometimes this can be non-linear. It depends upon the elasticity of the surface. We'll discuss it in the advanced part, but we can take it as a linear curve. Then it is easier for us to really control, make a feedback loop, because remember that we have to find a set point somewhere here. Anyway, we'll discuss it later. So somewhere here you have, so you can see that then the force becomes attractive, and then you go towards the zero force here. Uh, so this is very interesting schematic. I just love this, this schematic. So this essentially tells you the difference between STM and AFM. You can see the color-coded atoms. So all these uh, the light blue atoms, they are those atoms, really many of them, they participate into the atomic force microscope interaction. So all these light blue or whatever you call it, I'm not very good with colors. So when you look at the AFM, all these atoms will participate. You can see that the forces become so complicated. And also, for example, this atom and this atom may have a van der Waals attractive, they may be in the attractive region. Simultaneously, these two atoms may be in the repulsive region. Now you can see that some of the atoms of the tip might be interacting through in the attractive mode, but you have some atoms, so basically, so which are now, what is the simplest thing? So if you look at the this repulsive force is going to be much stronger. So in an AFM still, this force is going to dominate over these forces. But you can't ignore the forces acting between interatomic forces acting between these atoms and these sample atoms and tip atoms. But life in the STM is fairly simple. You can see that these red circled uh, atoms, they dominate, they are the atoms, they dominate in the tunneling current. So tunneling always automatically it finds the shortest resistance, the smallest resistance pathways. So when you're trying to do the conductivity measurement, so tunneling will happen essentially from these two atoms actually. So that is the advantage in STM over AFM. So in STM, life is much simpler. Even if you take a brittle tip or coarse tip, so there is no problem, because current find its own lowest distance pathways. So that is the advantage actually here. And this is mentioned in this force distance curve. If you see that this red curve represents the tunneling current, which is exponentially increasing. So you can make feedback loop easily for STM. You can calibrate it very easily. So this is this another curve is basically short range forces. This color matches here. Okay, you can these are all matching with each other. So now lesson is that AFM is feedback control for AFM is quite complicated, and this is discussed in this slide. And you must read this. I will skip it, but just to read this. AFM short range force is not monotonic, and it is difficult to design a feedback loop that controls distance by using the force. So now you can understand that it's not trivial to control AFM. Another problem is basically we'll go when we go much deeper, then we'll see that when we are in the contact, when this tip is in the contact mode of the surface. So mostly you use this Hertz model, because then surface deformation takes place, surface deformation of the cantilever, as well as surface deformation of the sample. And there are other complexities I won't go, because it depends upon how surface deforms of the specimen. that can decide the contact area. So contact area is not a static property, because contact area depends upon the type of surface. Suppose I take a soft polymer, and if I do the contact measurements, so when I'm pressing the soft polymer, so contact area will be very dynamic, because the moment I press more and more, so contact will that contact area will be changing, because polymer will deform as per the shape of the tip as you press it, and the contact area will keep on increasing as you press more and more, because tip is digging into the polymer. Same problem is for a biological sample. So there is no predetermined contact area, and so that you should consider. And there is a nice monograph by Butt et al. I think I already gave you the reference, which is beautiful actually, which basically represent many of these cases, day-to-day cases when we encounter in the laboratory. Suppose the surface is just a metallic, hard ceramic, then the life is much simpler, because you are not modifying that much the contact area of the specimen, because specimen doesn't deform that much. So when your specimen is deformable, then life becomes much more complex. Okay, because of the surface deformation. So that has to be really considered very intelligently. Otherwise, the calculation is going to run into several problems. And see, AFM, any technique is not like just you go blindly. And I told in the AFM, when I was teaching electron microscopy, I was stressing the same point, that don't become like a dumb researcher, basically, that, oh, this is my sample, and you just rush to the AFM lab, and bhaiya, kar do jara, I need one AFM. Which is, see, the life is not like that actually. It's not going to help you at all. Once you have to understand how the sample and tip talk to each other, the fundamental, then you can control, then you can understand actually what is going on. So I hope you might have you might have discussed, you might have understood these things, so that this is already discussed in past. So this is repetition, that capillary forces are sometimes very helpful for some of the modes, like dip pen lithography. For dip pen lithography, capillary forces are a blessing. For surface oxidation also, my personal experience is that when there is a humidity, you can it helps to oxidize the surface a lot. And so, as I mentioned, that this has been already covered, that this is the schematic which shows the distance between surface and uh, front atom on the tip, and your set point is somewhere here. You see this is set point which is there in the repulsive force mode. So basically you are pressing, and this is non-trivial. This is highly important. So if your set point is in the repulsive mode, that means your cantilever is slightly bent upwards. Okay, it's not relaxing. When it is relaxing, cantilever is relaxing, that means it is neither upwards or not nor downwards. So that means it's a zero force, so somewhere here, when you are at the zero force. So when you further press, so in when you do the atomic force macroscopy, when you say the set point, basically you're setting this distance, how much you, and it's basically your balloon height from the surface is exactly set point is here, basically how strongly you're pressing against the surface, and that decides your topography. You don't want to press it too hard and too soft. Uh, Okay, so this point is extremely important, and this is the chemical force range, quite close to the surface, and then comes our van der Waals force, which dies out around after 5 nanometer, maximum 10 nanometer. You won't get van der Waals forces, and more than that, you have electrostatic and magnetostatic. We won't discuss it in this module. Uh, so again, these forces are described that, as I mentioned, that you have to use the Hertz model, and there are other models too, depending upon the shape of the your tip. But okay, so, and this is van der Waals basically force 1/h square. Uh, Now let us move from here to three different modes. Uh, Outline you already have, because I have given the outline in the previous lecture, so it's going to be repetition again. So essentially, contact mode is basically you're dragging this sample along the dragging the tip along the sample surface, and cantilever deflection is measured, translated to surface force, surface shapes, and you have to be careful that you don't damage this surface. Non-contact is basically when the cantilever oscillates. I think I showed last time some animations. I can show those animations again and I can share with you so you can see them again and again. Some vendors basically they are nice enough that they keep the reservoir of these nice animations on their websites like NTMDT and many other companies. So it helps us also in teaching okay, through these animations. So thanks to their effort, their engineers' effort, that they provide us these nice teaching tools. Okay, so I'll move from here because this is already covered. This is already covered. This is already covered. So this is already taught. I'll skip it. I'll skip it. Skip it. Yes, this is important actually. This I should stop and then spend some time. So here we have to understand this is basically a summary of force spectroscopy. And what is now force spectroscopy? I can teach you. I would like to teach you without slides because I have an example to share. Then I'll move to the okay, so let us understand how this thing works. So, for example, I have a bowl full of sticky noodles, like Japanese kind of rice or noodles, whatever, not like Indian rice, which is not that sticky. So, and this is the fork, okay, very soft fork, and then you are bringing that fork in the noodle full of bowls, and when you dig into the bowl, basically what happens that these noodles are slippery and soft, and they will just adjust when you try to press the fork. Okay, and depending upon the how much you have cooked those noodles, whether those are soft or softly, I mean, quite overcooked, so they will be soft. They will get smashed. If they are nicely cooked, you know, like semi-cooked, like you have to bite those noodles. So then you may have to even if you press a little bit, they will not lose their elasticity, so they will get pressed, and when you remove, they will spring back. Okay, so they will not get deformed. So please understand the real life samples are exactly like that. So samples, when you press, they can get deformed like overcooked noodles, and they may not deform sometimes like undercooked noodles. So so when you try to so basically you, by pressing it, you can look at the how well those noodles are cooked. Okay, some noodles you may be able to press quite hard without deforming them, and some surfaces you may see that they are quite easily deformed. So essentially, you can measure the surface properties, you can measure the physical properties of different surfaces by doing this indentation measurement. So, for example, if I use my own hand, so you can see that this is a bony area, and if I press here, and if I remove, it basically doesn't deform. Okay, if I press it here because it's softer, so if I press it, it deforms. You can see that. You could see that it deforms, and then it slowly comes back. So real life samples are not very different from this. So this these are actually elastic properties of the material. So sometimes you can permanently damage the surface, and this is called indentation measurements. Okay, so so when you're trying to lift those that fork out of the bowl of noodles, what will happen? There, some of these noodles will stick to the fork, and you're pulling it out. You're pulling it out. What will happen? That after some time, after a certain length, okay, it is becoming hard for you to lift the fork up because there are some threads of noodles, lot of threads which are entangling. Some of these noodles will get straightened up, and shorter distance. First, what will happen that the noodles which are shorter in distance, they will break free. So one noodle which was the shortest in the distance, it can no longer get stretched because it's fully stretched. So now this will break free from the fork, and it will fall back into the bowl, and this cantilever will feel jerk the moment this falls back. Now you are because you are measuring the deflection, so you will record this vibration, this jerk, okay, and then at the distance from your bowl at which you felt that jerk will be the length of that noodle. Essentially, you have measured the length of the noodle because you know that how much you have moved up. Now you are moving it further. Another noodle which got overstretched will fall back, will break free from the entanglement of the cantilever. Now you are measuring another length, another length. So basically, this is basically you can make an analogy to basically the proteins. You are calculating the length of the different proteins, actually biopolymers, and there are several examples here. Another analogy, much simpler analogy for materials students will be, for example, this is basically a piece of uh, uh, this is basically spring. I don't have it here, but suppose this is a spring, okay, and there is a piece of iron attached to this spring, and this is a piece of magnet. This is a magnetic plate, and this is iron weight, uh, which is connected to the end of the spring. Now, these two things are separate. So this is your sample and this is your AFM cantilever, and which is nothing but a piece of iron, and this is magnet. Now, when you bring it closer to this, so because of the strong magnetic force, this spring will start opening up because it's getting stressed. So okay, when you're bringing that iron piece closer to the magnetic plate, what will happen that at certain distance, this magnetic force will become so strong. And please keep the analogy with the adhesive forces. Okay, so, it can be capillary force or it can be water wall force. That this will jump to contact. This magnet will grab the or spring will get will open up, and then this piece of steel will just get to the piece of iron. Okay, this is called jump to contact. At this distance, this cantilever or whatever it was, it will bend like this because it's like this. The force is so strong. So now you know that it is attractive force because it's bent like this. Now you are applying more and more force. Okay, what will happen that this spring will start compressing, and this cantilever will get straightened out. And certain time, at certain distance, there will be balance between the attractive force because you have also moved down. So this is at the relaxed condition. Fine, this is at the natural condition. Now, when you are pressing it further, what will happen that this spring cannot get compressed further. So that is basically pulsive reason. Now do the reverse thing. Now you're pulling this spring away. So then you have to apply more and more force because you please remember that this magnet is still attached to the piece of steel. Now you have to pull it very hard, and the moment it will just break free, there will be jerk actually, right? You have to apply really force, and this will jump back. Okay, so this is called jump off contact. So we'll see this thing through some slides, but I hope I give you two examples. And in this is called force spectroscopy. So you can measure so many things. So this is one of the richest uh, uh, experiment where you get so much of information, and this is quite complex also. So you have to take various measurements, and now you can see this is explained here. This I have taken from JPK technical notes, and all these things are acknowledged here in the footer. You can see. Okay, so now this is the red curve is basically approach curve, and this is actual curve, and you can see that this is the height in nanometer. So you can see there is no force range when you're approaching. That means there is no force. This curve is flat, and just follow the red curve, and you can see there is no force, zero force, and suddenly then you can see that there is an attractive force. This is called jump to contact. So as I told you that magnet and steel example, and once you decrease the distance further, then this curve will return to zero force because you are balancing it off. And if you decrease the distance further, essentially you are pressing the spring, compressing it further, then now you go to the contact region, or a repulsive region. So here you can measure the indentation. I explained you indentation is basically how much you indented, how much deep you can bury the probe into the specimen. Now the second cycle, trace and retrace, or whatever you call it, approach or retract, we're in the retract mode. So now when you pull the magnet away from the steel plate or vice versa, this curve will not follow the red curve. Now you can see the blue curve. So now you can see that instead of following, sometimes it follows the red curve. I teach it into this details. I teach it in different lecture. Different shapes of these curves will vary depending upon the interaction which you have. So this is not the case which you encounter always. This is a generalized case. Please note that the force distance curve doesn't always look the same, but this is one of the way you can explain. Now you can see that this has made a hysteresis loop, and this larger gap or hysteresis is basically because of the strong adhesion, because you have to apply some energy to break free of it. So basically, this area under the curve is your adhesive energy. So you can calculate the adhesion actually. Now this is jump off contact. Once you break free of this adhesion, this will go above the this zero force line, and then finally you have the zero force basically when you are quite far from the surface. And this is explained. Uh, Please mute yourself, Sanket. Yeah, Sanket, please mute yourself. Yes, so it is written here. I think you can read this. I don't want to read this. So I have already explained. Okay, so now what information you get in the approach curve when you are really far from the sample in several tens of or hundreds of microns, you have no interaction. You are not measuring any force, but once you start approaching the specimen, the first thing you encounter is basically long range electrostatic and magnetostatic forces, whatever it may be. And once you bring the tip far closer to the surface, for example, nanometer to atomic distances, then one of these forces, whichever is dominant, will start basically interacting. Whether it can be van der Waals force, attractive parts. Please note that attractive parts of part of the van der Waals force and van der Waals interaction. Capillary forces are enemy. Capillary forces will be there in this weather in Pune or Mumbai or anywhere else in this part of the subcontinent. And this part I have actually not taught. Maybe in advanced module I will reserve. I mean, this is interesting. To know about the capillary forces, and this is becoming more and more interesting actually. But some people may be uncomfortable with going into too much of detail, so I have skipped those. I didn't teach actually capillary forces so far, if you remember. Normally I teach, but this course I thought that let me jump to the AFM module modes rather than van der Waals force I covered nicely. And then you can have a screen electrostatic forces. I will be teaching this in aqueous solutions. Okay, and then you can have magnetic forces, chemical potential, solvation forces, and so on and so forth. So basically, you in the contact mode, you get the information such as stiffness, Young's modulus, and we have done in our group. We have done a lot of work. We have published a lot many papers in this domain. And then in retraction mode, you can measure ligand receptor interaction, antibody. I give example of the SARS coronavirus, right? And DNA hybridization, you can look at the specificity of, suppose you take two complementary strands of DNA, okay? And then one strand is at the surface and another strand is attached to the atomic force, the cantilever tip. So then you can look at whether they are matching or mismatch or matching, the strands, the amino acids. So you can look at the protein folding, unfolding, pulling out of membrane. We have done a lot of these experiments in our own lab also. DNA stiffness or melting. Melting is basically you try to melt off two strands. So there are a lot of basically examples you can think of. So this has been already covered. So I'll skip it. Let's go deeper into now having understood the basic interaction. Now we are ready to go deep into detail contact mode imaging. So contact mode, basically there are, you will be seeing it in the next lecture. Actual hands-on, you will be given the software which you can install in your own computer, and we'll give you example files, and then you can play with uh, um, the basically the images, and it's fun actually. Okay. Yeah. So what is the reason that vertical resolution is best in the contact mode? I think we have already discussed this, because we are looking at the repulsive part of the force curve, and which decays very fast, 1 over r to the power 12, all of you know, and that gives us high amount of sensitivity. So we are basically in contact mode. We are somewhere here, okay, and it falls off quite fast. You can see as a function of distance, this is falling very slowly in comparison to the force here. So that makes it, because dv over dr or df over dr is quite fast, or d square v over dr square is quite fast, quite large number. The slope is quite high. So that makes it highly sensitive. That question, answer to that question, right? This is already covered. The tip, it is V-shaped tip. Now, this is quite important part, that you get three information. Height data, which is basically change in the piezo height. I think we learned that there are two modes: constant height mode and constant force mode. In one mode, constant force mode, you keep the feedback loop on, because you would like to move the cantilever up and down, and your effort is that you would like to keep the force constant, and there the feedback loop is on to keep the basically force constant. And another mode is basically constant height mode, and that is reserved for smoother samples. You would not like to use that for rough samples. And this is the constant force mode, is the mode which is usually used for day-to-day samples. So there you get, in one shot, you get three informations. Basically, you get three boxes. I will show you in a minute. Some students had this question, curiosity, that what kind of information we get. So unlike in AFM, unlike in TEM, you get one image at a time, and that's what you get. And here you get, you can get in one scan, you can get multiple information. These are the basic things which I'm teaching. If I go to the advanced level, you can see that you get 7, 8 different information in one shot. That's the beauty of AFM actually. So you get the height mode, which is basically piezo moving up and down to keep the cantilever deflection constant. Please remember feedback loop. And second information is deflection, because if the sample is too rough, that then what happens, that we are not able to, feedback loop is not able to keep the deflection, cantilever deflection constant at the set point which you have determined. So you end up getting some data here, which is very useful, which is also called error signal mode. Okay, this deflection. Okay, fine. Third thing is twisting of cantilever. I think we have already discussed. So this is the lateral twisting. Please remember quad photodiode, which splits into 4 parts. So I think you remember A plus D minus C plus D. This is A plus D minus C plus D information. And this is A plus C minus B plus D information, right? The lateral movement, that gives you the frictional information. So this is the representative data from one of our users. I don't remember what sample it is. Probably these are carbon nanotubes in a polymer sample, polymer matrix. So what is interesting for you? Let us understand how these images can be interpreted. For the students who are starting from zero, I would like to spend more time, and advanced users or senior people may find it very boring, and please excuse me for that. So if you see this, there are three pictures, and the scale is from 0 to 1.5 micron for all these three images. And just first ignore this bottom row. Let us focus on the top row. Basically, this is the scan size is different. That's the only difference. You can see that scan size is 1.5 micrometer to 1.5 micrometer. Here, the scan size is around 4 micron to 4 micron. That's the only difference. But just ignore this. And this is the zoom view. Now, these colors are fake. You can choose any color. Okay. And let us understand the first colors. So you can see that this 100 nanometer, the top color, the lightest color, or whatever the pinkish color is, represents 100 nanometer, and this represents for example, zero. This is a relative scale. Okay, this scale has come from the force measurement. Please remember, based on the deflection sensitivity of the cantilever. So now you can see that these darker areas are somewhere here. So once you draw the line, it will show you exactly what is the roughness of the samples, what is the distance from here to here. You can do all these measurements here. So essentially, this is purely topography of the sample. Now, if you move to so this basically came from up-down movement of the cantilever, and that means deflection. At deflection, and the feedback loop tried to make the deflection zero by moving the piezo up and down. Okay, changing the balloon height. Got it? Just remember balloon flying over Pune surface. So this distance was calculated how much balloon has to move up and down. For example, this is a tall area. These are basically some hills, and you can see that. So that means balloon had to move somewhere around 80 nanometer to adjust this height. And these are the deep crevices. So there, balloon had to really come to this height so that the set point, what we have decided, can be maintained. But if surface is too rough, then you know that cantilever deflection. So if the cantilever deflection is essentially zero, the feedback loop is perfect, then this should be featureless. There should not be any data here, right? Deflection should be zero, because in the constant force mode, please remember that constant force means no deflection in the cantilever. From where this information comes? See, depending upon the feedback loop, how closely you scan, what are the parameters you decide for feedback loop. This depends upon PID parameters. So just imagine that you are sitting in the balloon and you are flying over a rough surface. Now there are three ways you can increase the or decrease the gas, hot air gas. One is basically you calculate the distance. For example, your distance is supposed to be 50. Now it has become 60. So proportionally, you can increase. So the difference is basically 60 minus 50, basically 10 meter away. So you can decide a mechanism. Okay, when this 10, then I will move it by 1 notch. And if it is 20, then I will move it by 2 notch. Okay. So that is proportional control. Now, integral control is basically you're not taking. So the problem with this integral control is that your balloon may overshoot. You are trying to keep it 50, but it may come down to 40. It may come to 60. So that is the problem with the proportional control. Now, one smarter guy will do will monitor. Okay, let me see how this hill is moving. Let me see for some time. Then only I will integrate over a period of time. That is called the integral mode. Actually, that Okay, balloonist, what it does basically, it looks at for certain time, and then it takes the decision how much. So that's the second control integral, and then differential. Basically, you look at the slope, and then okay, and then you decide another control. So these are finer and finer control. Normally, P and I are used. So if your control, sometimes you want to make control too good, then that can be very rough ride. So basically, so for example, you are making too fast measurements, so your balloon will constantly keep on moving up and down, and that ride is not going to be smooth, right? It will be very bumpy sometimes. You're you have too much. You're controlling too much. Okay, so when you do the actual AFM measurement, then you get the feeling. I can just tell you the analogy, and that is the reason that, oh, you have tried your best, but still the cantilever is deflecting. So then, because of this roughness, then you get this deflection information, and this is very useful. So you can see that you get to see those area which are extremities. You can see, actually you can see this is extremity here, you can see it here, and the deep valleys you can see here, you can see here. This is friction. So if your material was made of, your sample was made of one material with no basically frictional friction. For example, it was equally smooth. Then you should not see any information here. The reason that you see some information in the friction force microscopy, that means surface was not equally smooth because of blend. Actually, it is carbon nanotube and polymer blend, and within a blend, you can make surface much smoother depending upon the casting actually of the sample. For example, it was probably a drop casted sample, and so for the same polymer, you can make the surface smoother or rougher. You know it quite well. So that information will be covered here, and that is because of the lateral movement. I already explained in the previous lecture. If you've forgotten, you can go back to the recorded sessions of the previous lecture, and then there you can get this idea. This is already taught, that constant force mode. And next is constant height mode, where the piezo is kept fixed and the deflection is measured. And that is faster because you are not worried about, you are not basically changing the balloon height. And that is very risky. It is okay if you are flying over some flatter areas, okay, where there is no mountain. But so there you can safely adjust one height for balloon or whatever gas conditions, hot air gas condition, and you can keep on going. No problem. You are at ease. Maybe some smaller differences there that you can take care. So this mode is reserved for those kinds of situations. Okay, and this is the recap of constant force. As I mentioned, that to collect the height data, it's called feedback gain. Whatever I told you, the tighter control, proportional integral must be very high. So tip tracks sample surface with minimal cantilever deflection. Of course, there are problems associated with that. So this is the image which was taken by one of my students. I do not remember, probably Umesh or Ramya. You can see these are actually marine bacterium, and you can see two conjoined bacterium, and you see another bacterium is basically budding from this one. And if you notice, I'm not showing image number one, panel number one. I'm showing panel number two, which is deflection. And this is 10 micron by 10. Another thing which I forgot to mention, if you notice that here we have height information in units of nanometer, but if you notice here we do not. Uh, Here these color codes are in millivolts. There's a problem. Can you convert this into the length units? Yes, you can do that. and this is basically frictional force. So this is not a length unit, but this can be a length unit depending upon the roughness. So that I will tell you how to convert that. That will be later on, because you need to do some calculations by yourself to convert this into from millivolt to which we call deflection sensitivity and other things. Okay, F is equal to minus kx, Hooke's law, all of you know, so that information comes from this. Essentially, the AFM controller records the information in millivolt, and this millivolt information data is coming from the photodiode. Photodiode basically transfers the laser signals into voltage. That's it. That's why you have the voltage information. As simple as that. This is such a beautiful image. You can see all the surface structures. You can see these, what do you call it, pili or something. Some of the, I think if some of your biologists, then you can comment on that. Okay, and so this is quite useful. It's quite useful actually. Let us jump to the constant height mode. Constant height mode, feedback loop is off. It's basically a nice smooth ride without much दिमाग नहीं लगाना ज्यादा है ना इसमें ज्यादा परेशान नहीं होने की जरूरत नहीं आराम से no piezo movement. Okay, your cantilever is deflecting absolutely no problem. So this is not usually used, but it is important to teach. So I will move this another place. So, and as I mentioned that this mode is especially for thin films, deposited thin films. One of the example is gallium nitride film. You can see that this is quite smoother film. And look at this scale. Uh, uh, there we were talking about quite rough samples. Here, let us see. You can look at the scale. Here it was 100 nanometer, 130 nanometer. And in this image, we are talking about few nanometers. You can see 3.5 nanometers. So now you understand what I was trying to tell you all this while, that this a constant height mode is reserved for relatively smoother samples. So you can see that step heights you can measure here, which are around 2.5 angstrom or 0.25 nanometer. This represents one layer of gallium and nitrogen atom. You can see that AFM has ability to measure very small height changes on the surfaces. So this is the beauty about the Z resolution is very high. This collagen fibril is another information. And yes, this is carbon nanotube grafted with polymer. Okay, so there are tons of examples. You can see these are silver nanostructures. These are from our own lab. I think this was published. This was probably Silva Kulkarni's former professor. Her samples we received. So you can see that there are different scale, 2 micron by 2 micron, 500 nanometer by 500 nanometer, 1 micron by 1 micron. So I've kept some of the images for you. You can collage, you can browse through them. I'll move to the next one. Lateral force frictional analysis of surfaces on nanotribology. I don't know how much of you are interested in this mode, but this is quite interesting. And I have already taught you a lot about this, that one way is that you look at the vertical reflection, okay? And another way is that you also capture the lateral deflection, like the twisting and so I think this is already covered last time, that in the animation I taught you. So I'll skip it. You can browse over this. Yes, problem with contact mode. What are the applicabilities? So this is taken from Barga and Ricci book. Another book is there, Atomic Force Microscopy, Biomedical Methods and Applications. Okay, So in contact mode, the problem is, especially in this weather, you have quite a lot of adsorbed water layer. This can be few nanometer water layer. You don't see that water layer, but almost all the surfaces, depending upon their hydrophobicity and hydrophilicity, if they are hydrophilic, then you will have quite a lot of water there. So, so you can see that there is a capillary forming between the AFM tip and the sample, and because of that, you can see there is a this cantilever is bending downwards. So, contact mode, no doubt, it is extremely high resolution, and dynamic modes can also achieve extremely high resolution, but contact mode resolution is quite high actually. So, but liquid cell imaging in water actually, suppose you, so how to avoid these capillary forces? One way is to, uh, so how do you remove this capillary force? So, so one way is that you fill water all around this. Basically, you dip entire thing with water. So then this capillary is gone because it's all of it is submerged into the water, and that is precisely what we call liquid fluid cell imaging or liquid cell imaging. There you can use this mode without having to worry about capillary forces. Shear forces are very high. So you can see this polar bear, dragging the body. So that is disastrous for soft samples. Uh, but still, you can manage the smart users, experienced users. My own students uh, got wonderful images of very soft sample like biological uh, samples like cells. On from contact mode, there was no problem because their hands were so trained. Uh, they never faced any problem. So that depends upon the set point, uh, what you said, and so shear forces may distort features in the image, and capillary forces we have already discussed. So that these are the problems with the contact mode AFM, as it is described that you can have uh, uh, vertical forces, which we are already discussing, and in addition to that, you have the lateral forces. Uh, and this force is applied all the time. You can see that this force is you are applying this force all the time in the contact mode, while in the tapping mode, only in a very small time domain, you come into contact with the sample. So this vertical force is applied only, there is no shear force. So this force is gone in tapping mode or in the semi-contact mode. You do not have shear force, and this vertical force, this vertical banging of the sample is happening in a very tiny time zone. So basically, you get rid of shear force altogether. That is the beauty of the next board, which we are will be discussing. These are some of the yeast cells. Actually, again, we published paper from this. You can see that we were able to get beautiful images from the contact mode. Absolutely no problem. So counter my own slides, I thought that to put those images, you can see the height mode, deflection mode data here. Absolutely no problem. Uh, See, the challenges becomes opportunity, as our Prime Minister always mentions that the smartness happens when you convert the problematic areas into the challenges, and that exactly happened in the dip pen lithography. That using this capillary, one new mode was developed that you can do this molecular transport. So you can attach these molecules, and depending upon the meniscus size, water meniscus, you can write molecular. It's like a molecule, your fountain pen. Uh, So if you pull this AFM tip away slightly from the substrate, you can see the size of the meniscus becomes smaller and smaller. If you pull it downwards, then the size of meniscus becomes larger and larger. So that can control the font size, for the width of the font. How, if you want, basically, what is your tract size? Okay, that's this very smartest application. Okay, next is basically dynamic mode, dynamic modes. So, force modulation, I will not be teaching now, maybe in the next lecture. Um so let us look at the tapping mode real fast, and I'll show you some animations. Uh, let's see. If you cannot see, please alert me. I think you can see these files. This is intermittent contact mode, or tapping mode, whatever you call it, or dynamic mode. They are amazing. I mean, you get a lot of other information also. So let us play out this video. So here your sample is there, and this is the cantilever. And as I mentioned that normally these cantilevers are beam shaped rather than V shaped. And another thing that these are very rigid. Spring constant is quite high, around 10 Newton per meter, or around that range. Uh, they are made of silicon, rigid material, but also brittle. You can afford to take them brittle because you're not touching the surface. And you don't have the lateral and vertical forces that strong as you have for contact mode. So there is a piezo sitting over here. There is a piezo drive here, so which basically oscillates this tip up and down. So you might be wondering what basically oscillates this tip up and down. So depending upon the resonance frequency, slightly off. It's called cantilever tuning. So you basically tune. It's like, you have the tuning fork. So you basically first you have to tune that cantilever near to its resonance frequency, not exactly at the resonance frequency, slightly shifted. And once you, and typically it is in kilohertz, few kilohertz, 10 kilohertz, probably 100 kilohertz. So that's quite fast. So that means you can see that almost 10,000, 20,000 rounds in a minute, in a second. Okay. So, and when you look at these oscillations, so there is another thing, amplitude. Amplitude is quite large. It's around 100 nanometer. What do we mean why do you need 100 nanometer? Because you have to break free of those strong capillary forces. And another thing is that you are mapping both the attractive and repulsive regions of the force distance curve. So that's why this amplitude is kept really high. In contrast to the non-contact mode. Non-contact mode, this amplitude is kept quite small, around 10 nanometer, and here it is one order of magnitude hard. Now, once you bring this tip closer to the sample, now there is no force between them, but the moment this tip starts feeling force between the sample and tip. It can be any force. It can be electrostatic, magnetic force. It doesn't matter, depending upon your sample. I'm not commenting on that. But what will happen? That there will be change in the amplitude. This force will try to drag it. And if you see that this force is constantly changing, it's not like, unlike in contact mode, because this is vibrating. So basically you are taking a derivative of force all the time. Okay, because this is basically this is going in and out of that force curve from different areas. This is passing through. So there will be reduction in the amplitude. So A0 will become some A, And also there will be phase shift. Phase shift means when this piezo drive is it wants to uh, shift the tip up, you are somewhere here. So actual condition, the tip may be somewhere here. So that depends upon the adhesive properties. Again, you are basically it gives you, and also there can be change in the frequency. So we are not considering the frequency change. We are considering the amplitude change as well as phase change. And so phase change depends upon the adhesive properties of the sample, not the topography, but the roughness and no, sorry, adhesive, mostly adhesive information actually. So now if I activate this, you see this A0 has become ASP, set point. So this is your set point, and you're trying to, again, you are applying feedback loop, and you're trying to see it is scanning the topography. And same thing, similar to what you did in contact mode, you try to maintain certain distance of the balloon with the surface. And here, that is basically specified amplitude which you are trying to maintain. And any deviation from this predetermined amplitude will result into a trigger to the feedback loop. Okay, it is time to move tip away from the specimen or towards the specimen, depending upon what kind of a, uh, uh, changes are discovered. Basically, suppose amplitude is larger than ASP, then it will say, okay, come down, bring the tip towards the sample. And suppose the measured amplitude is smaller than an ASP, then okay, you pull back, something like that. Those shouts are heard by from the controller to this instructions are given, and then piezo works accordingly. So that basically decides the topography. It represents the topography of your specimen as it is mentioned. So let us do it again. A0 is the free amplitude. ASP is basically your set point, and you see that you would like to maintain this, and that represent into that basically translates into the uh, this kind of topographical measurements. Similar to what we saw in the contact mode, you here also you get uh, three panels. So let us discuss the second panel, phase imaging. There will be change in the phase as well. And so, so suppose there is a blend of polymer. So these are two patches which are of different material. So there you can see that you're trying to match this, but there will be a phase lag also. So this green line and blue, this will be, you can see this is shifted now. As soon as it came here, now it is shifted back. There is no phase change. Now there is a phase change. So in addition to the change in the amplitude, you will see the change in the phase, and that represents uh, change in the material type, not the topography. So it is basically beyond topography. So AFM basically tell you the change in the type of material. So I do it again.
Sir, it is not visible in the screen.
Oh, what do you see here now?
Just your screen that phase imaging the three videos.
Oh, you don't see this. Oh, I see. I'm sorry. You don't see the video?
Yes, sir.
Oh, it's good that you told me. Let me do something else. Can you see now?
Yes, sir.
So this is a phase imaging. You can see it again. So this, you can see that in addition to the topography information, uh, so this is giving you pure phase information actually. So let us look at the other one. Probably you missed it out. So this mode is so you have this free, this is called free amplitude, and this is called amplitude when you are in touch. This is called set point, SP, and you can see that it is giving you purely topography. Fine. So this panel or this information is not sensitive to the material properties, but it is definitely sensitive to the topography alone. And let us go to the third panel, which we normally see here. And yes, so this is called error signal. The same way we had, I think you saw that bacterium images. So if you have any sharp change in the topography, so then you get these blips actually. I think we saw it in the other cartoons also in the last lecture. Yes, I repeat it. So you get this error signal mode, okay, because of the strong rough features which you have. Because cantilever is not able to adjust to this sharp bumps. Uh, so that results into the error signal mode, and that is not bad. I mean, it gives you rich information about your sample. Okay, so I will recap in the next lecture. So I normally don't go too fast because there is no shortcut here for these things. So if there is any question, I would like to take questions rather than jumping to the next topic. Uh, Let us go slow. It's better. So I stopped sharing. Let me stop the live.